chose the equatorial C-ring mount because it's more compact, has a higher resonant frequency, and that gives us the ability to move the telescope pretty quickly, stop at a target, and have the thing settle down in less than a second. Here you can see the RA in action, just as we saw outside. The C-ring rests on 2 rollers, as seen here and on the other side. Each roller is driven by a direct drive motor, as shown here. And a gold tape scale here gives you the on-axis encoding. Here you can see beneath the cover the drive surface, the encoder surface, the motor, and then we have a novel cover we call the bug cover, which is like a conveyor belt that follows the C-ring as it turns. Here we have the pneumatic brake for declination, limits, and our cable routing is done internally through the center of the axis here. Both sides of declination have cables running through them. They go into the C-ring, route internally through here, and come out the back, and then go through the RA axis into the control panel. So here you can see the right ascension drive motor at this location. This is driving a roller, which is, I'm going to make a slice here. So you can see the roller, the C-ring is supported on 2 rollers. One is an idler and one is driven by that motor. And there's a gold scale at this point as well that gives you the encoding for that axis. The read heads are inside the cavity here and here. And covering the whole thing up is what we call the bug cover, which is wrapping around the outer diameter of the C-ring.
So on this 1 meter mount, we've got a drive system that closes the servo loop kind of at 2 levels. We've got an off-the-shelf drive solution that closes a servo loop to gold encoder tapes on each axis at something like 1,000 hertz. That will position the telescope statically to any position that we want. The dynamic portion of the servo loop is handled by the telescope control system and the MIC level software, where a progressive demand is supplied over time and closed using the off-the-shelf drive solution. The slewing mode of operation is actually very similar to the tracking mode for the RA axis, but the demands are just supplied in much smaller chunks. For the deck axis, however, it's quite different. The deck axis actually moves a very small amount when we're tracking a target because this is an equatorial telescope. So we can't use the same velocity demand that we use for tracking and slewing with the RA axis. What we do is we supply an absolute position demand and keep it basically fixed as it tracks the target, and only correct in very small increments for things like tube flexure and problems with the mount model.
This is the primary mirror support. This is the central hub, where the central hub for the primary mirror sits. It bolts to that. The instrument bolts to this back surface here. So that's where all the instrumentation goes. It locks in there. And then these 6 pads are where the whiffletree support bolts on. And these 4 pads are where the truss mounts too. The mirror cell, the blue trunnions here, the C-ring, the sandwich, the base, it all gets assembled and aligned and shipped to site as one unit. So there's various holes in the back of the mirror cell. These are access holes to unclip the primary mirror to remove the mirror for a recoat. This hole here is for fans. You can put up to 12 fans on the back of it. This fan just slides right in there, and a filter goes on the outside. The primary mirror and its hubs can be removed from the mirror cell easily with these 6 clips. You just unclip them and put them in. So these access panels in the mirror cell are spots where you remove the panel. You get to the cabling, electrical cabling inside here, either to remove or replace or implement something new. And those can be easily accessed through 10 panels around the side of the telescope. So as we saw in the shot, this is the primary mirror cell. You have the mirror cell here with the panels on the outside and the primary mirror there. This is with the mirror removed. You see the whiffletrees there, 18-point support with the central hub right there, fans, and panduit along the outside. That's a cutaway section of the assembly. We have little mirror clips. These actually hold the central hub and mirror onto the mirror cell. This is our 1 meter OTA. It consists of an instrument, mirror cell, mirror cover, trusses, secondary, and focus mechanism. It weighs about 1,200 pounds, about 550 kilos.
For the OTA, we use carbon fiber trusses for stiffness to weight ratio. We have aluminum castings that are machined for the nodes. There are Invar vanes, and then the top end provides tip tilt for collimation and then focus. I'm showing a model of the OTA that we saw in the shop. You can see the trusses, the top nodes, offset vanes for rotational stiffness, and then a flexure-based mechanism to focus and tip tilt the secondary mirror. We use finite element analysis to look at the vibrations and deflections of the different components of the telescope. Here I'm showing the first mode, which is rotation, and this shows a large exaggeration of the deflections we actually see.
So what we have here is the ray diagram for the 1 meter telescope. We have light that comes down from the stars, hits the primary mirror first, is reflected, hits the secondary mirror, comes down through the hole in the primary, through 2 doublet lenses, through a filter and then a field flattener, where it then finally hits the CCD. I also have shown a placeholder for an auto guider pickoff. They'll go to a separate camera. If we go over to this window here, we have the spot diagrams for the telescope. We have shown 82 millimeter square corrected field of view, which is approximately 1 degree corner to corner on the sky. The spots are exaggerated in size by 1,000 times. You can see the area disk in the center. And we have drawn 400 to 1,000 nanometers in wavelength.
This is basically a small brother version of the actual panel that will control the 1 meter telescope. It will accept AC power and Ethernet from the site services and provide all the functionality necessary for the 1 meter telescope to collect images and collect data. It consists of a couple of basic sections: the AC power processing and switching, DC power supplies, computers, and servo drives. We have 2 computers. One will process images and get them back to the network. The other computer is responsible for all motion control on the telescope, and then the servo drives are what actually drives the motors on the telescope and controls positioning.